I'd like to introduce Melinda Thielbar, our President Emeritus of the RTA. Melinda and I have worked together on and off for many of the last, I don't want to say how many years. She's smart as hell. She's a very interesting speaker. And if you haven't had the treat of watching her explain something complicated, buckle up and please enjoy.
Awesome. Thank you so much, Dan, for that very warm introduction. All right. So I asked the RTA board if I could give this talk because this is the first piece of software that I've been really excited about in a long time. So this is Tensorflow Probability. And the amazing thing about Tensorflow Probability is that you're finally able to do all the things you feel like you should be able to do when you're modeling a complicated problem. Okay. So what do I mean by that? Well, when the folks who built TensorFlow Probability first introduced it on their blog, their example is actually a lot better than anything I could come up with. So I'm just gonna hop on over to there and show you this very simple example that they come up with. So what you see, that first red line is a basic regression line, right? So let's scroll down a little bit and take a look at their first attempt to fit it, right? Everybody who has ever done data science has done this. You fit a regression line, it looks like a straight line. If you've been pushed and prodded through an advanced couple of statistics classes, you know that that regression line goes through the mean of y at every x. And you also know that this is the wrong thing to do because this has a problem. It has a fancy statistical word that I remember teaching everyone to pronounce back when I was teaching graduate students, and that is heteroscedasticity. As x gets bigger, y gets bigger, but the variance in y also gets bigger. And that's not okay. It messes up your hypothesis tests. It understates the formulas that you get out of most statistical software packages will understate the variation in y, and it will give you bad confidence limits for your predictions. And so when we're out here at x equals 50, your confidence limits will not cover that whole range of those little blue dots, okay? Now, when I was first teaching this for SAS, people would ask me, well, what do I do about it? I would tell them how to detect it, and they would say, well, what do I do about it? And the tools were not great back then. I would say, oh, well, you could take a log transform, that might solve your problem, or maybe a square root, or... But the thing is, what you really want to be able to do is tell the computer, look, fit the mean of x as this, fit the mean of y as this increasing function of x, but also fit the variance of y as an increasing function of x. Just tell me how big the variance in y gets as x gets bigger. And there's not a lot of clean ways to do that in the 21st century, which is kind of annoying until TensorFlow Probability came along. And TensorFlow Probability came along and they said, well, look, tell you what, yeah, you're gonna fit this normal, but you're gonna fit this normal with a mean, right? But you're also going to fit this loc equals t is actually so cool. This loc equals t is actually a prediction out of a complicated model that fits the mean of y. I say loc equals t, I can also say scale equals t if I want to, and I'll show you how that works as we go along. This is the first software package I've ever worked with that just lets you say, hey, look, I know the variance is also an increasing function of x, so here, the variance is an increasing function of x, and the software pretty much just handles it, okay? And that's really amazing because now I can fit this fan shape in a way that makes sense, where I'm directly telling the computer what to optimize over and the computer knows what to do. Now that's awesome enough, but the secret that isn't really shown when you just do the scatter plot is that that's not actually a fan-shaped mean. That's not a Y that has an increasing variance. This is actually a Gaussian process. And if you're a scientist or a mathematician working with this team, chances are you know that that underlying process is a Gaussian process. And yes, with TensorFlow probability, you can actually fit that wiggly line. You can say, okay, yeah, the mean goes up, but there's also this, this movement, this periodic movement in Y. And you see, when you do that, you fit this piece of code, or you fit the Y almost really beautifully. In the old days, this was a giant headache to fit. In TensorFlow probability, you can do this with a few lines of code. And it has all the advantages that TensorFlow has, which I will talk about as we go along. Okay, so why am I giving this talk, and why am I so excited about this? Because this really is kind of a breakthrough in terms of what you can do with software. By the way, Dan, I can only see my own screen, so if there's a true emergency, I'm going to need you to interrupt. Otherwise, I'm just going to assume everybody can hear me and we're fine. Okay.
Yeah, so far, the only question was around comparing this to something like GlimMix, right? The generalized linear mixed model procedure.
That is a really good question, and the short answer to that question is there is a GLM package that's part of TensorFlow probability. It's actually a new part of TensorFlow probability that works for generalized linear models. But TensorFlow probability is so much more flexible. And I'll show you actually right now what the flexibility looks like. So what do I want? So what problem has been keeping me up nights? The same problem that's been keeping a dozen amateur scientists up nights. How fast are COVID-19 cases growing right now, right? And what does that tell us about what we should do next? Some of you might have seen Kevin Systrom's blog about this, where he talks about R0, which is the basic reproductive number of coronavirus. Systrom's blog is really worth reading. But basically, in that blog, he comes up with a method to fit a real-time reproductive number for the coronavirus based on changes in case counts over time. And he has this website where he has everybody kind of stacked up from smallest current RT to largest current RT. He's got error bars on it. Okay. And he also has kind of this idea of which values are in control. Although if you do control charts, somebody should call him. Tennessee is not in control. You can see where the error bar is. It's above 1. But okay, you know, he founded Instagram, and I work in a tiny office at Fidelity, so I guess my opinion doesn't matter as much. However, you could not fit these numbers with a standard linear model. It would not be easy to fix these numbers with something like SAS's GlimMix. It would not be straightforward to fit them with RStan, though you could probably handle it. It would not be straightforward to use something like WinBugs. I have used WinBugs. It is a really nice tool for what it is, but what I want to show you is how simple this is by comparison. If you've used any of those in the past, I think one of the things you're going to see is how much easier this can be. So Kevin Systrom publishes this article, and he's like, hey, I think I found a way to track R in real time. And he shows on his, he shows his code to do it, right? But here's the thing about Systrom's code, which I have a link to here. The equation that Systrom wants to fit looks like this. For the math nerds in the audience, you will notice that that is a Poisson distribution. What he needs is lambda. Lambda is the parameter that tells us how many new cases we can expect given a smoothed average of yesterday's old cases. There are ways to fit Poisson distributions and get lambda out of there. You can code up the likelihood function, whatever. And Systrom's blog actually goes through his own kind of brute force algorithm, and he derives this really nice likelihood function. He derives the posterior, and then he actually like optimizes it. And the optimization is not like what somebody who was writing statistical software would do, but it's a very succinct and elegant solution to that problem. But it requires an entire IPython notebook worth of code and some fairly lengthy derivations. Like here's his get posteriors, right? This is how he actually gets the likelihood function. And it's these massive lines of code. And it's not so much that it's a lot of code, all right? It's a lot of code. You would have to write that code and you would have to maintain it if you were gonna do this in production. But the other thing is it only works for this problem. And so if somebody says, well, maybe you should try fiddling around with this a little bit, maybe instead of a Poisson distribution, you could consider that maybe lambda comes from a different kind of distribution. You get another Bayesian layer out of it. None of this works at that point, right? None of this code will actually make that happen. You would have to pretty much start over. Here's what you would do in TensorFlow. So TensorFlow, Systrom does all the data prep. The blue line that you're seeing is a smoothed average of the number of new cases over the past 9 days. It's a Gaussian smoother, so it weights cases that are kind of coming up in the middle of that 9-day period heavier than cases that just happened. The idea then is to use this smoothed rolling average of the last 9 days as a predictor for how many cases you're going to see today. Okay, so you've got a kt minus 1. K is your count. Why don't we use c? I don't know. They never do. K is your count. Kt minus 1 is the smoothed average of the number of new cases that have shown up in the last 9 days. KT is today, and I want to use KT minus 1, this smooth blue line, to predict KT. And from that, I'm going to pull this real-time R0 that's going to tell me, he calls it RT, because obviously it's not R0. It's going to tell me, is this state controlling coronavirus, or are they not controlling coronavirus? Is it in control or out of control in this area? Okay. And so these are the new cases per day for New York, which is pretty interesting. The new cases per day for North Carolina are over here. All right, you can see we have not see New York has this kind of nice, wasn't nice very recently, but New York has started to level off and come down, and you can see North Carolina really hasn't. And what we want to be able to capture is, are we in that period where we're leveling off and coming down? Or are we in that period where things are still kind of heating up? Okay, that's what I want to know. We have decades of research that kind of tell us the relationship between current cases and new cases. We know for a fact that that number is not normally distributed. We know for a fact that a linear regression isn't really going to handle this. Yeah, you could log transform and what, but why would you do that when like modern tools will let you not do that? Okay. So we're going to import TensorFlow Probability, and we're going to import something called TensorFlow Probability Distributions, which is their distributions package that lets you specify all of these exciting models with all these different ways of looking at the variance in Y. And then we're going to do some data work to convert all this stuff to tensors so they can go into TensorFlow. If you're a TensorFlow nerd, you're probably pretty used to seeing stuff like this. For those of you who've never used TensorFlow before, basically TensorFlow has all its own data structures. It is written in Python. It's Pythonic, but it is kind of like its own language. But the important thing here is that I'm getting that rolling average, and I'm only going to do this for New York. I'm getting that rolling average, KT minus 1, and I'm getting KT, which is today's case count, as tensors that I can then port into TensorFlow. Software developer, you never do anything without a unit test. Those things have got to be the same shape or everything crashes, so I check. I want to know how big that vector is, so I check out its shape and print it, okay? And in this case, I have, for New York, 47 time points, okay? All right, gonna pause there for a minute. Dan, are there any burning questions in the chat?
So far, the follow-up to the Glimmix question was, what about M, G, C, V in R, which I don't think I could spell again without looking at it. So I don't know. I don't want to put you on the spot to address that if you're not familiar with that particular package.
I am not familiar with R. I'm going to let Ian Google and come up with that at the end of the at the end of the presentation.
And then there was a request to publish your notebook when all is said and done.
Sure, as long as you promise not to link Kevin Systrom to it and tell him that I said that his stuff isn't any good. I don't want to be in the middle of that particular battle.
Don't at me.
Yeah, exactly. But yeah.
Yeah, and there was a general note about sort of data quality in general, but I'm taking data quality as read, and you're going to do stuff with the data that you have.
Yeah, no, data quality keeps me up at night right now. Yeah, I know the data's crap. It's all crap. It's probably better to use, it's probably still better, sadly, to use the number of people who've died and growth in the number of people who've died and then extrapolate back to cases. There are a lot of people doing a really good job with that, and there's no need for me to recreate their work. But Systrom points out kind of rightly, this will be sensitive if you're ramping up testing during that period. But if your testing rate stays pretty constant and your positive negative rates stay pretty constant, this actually does okay. My main worry, honestly, when you look at this, is the reporting, right? There's no way, there's like, I've got stuff in here where it's like 2,000 new cases in a day, and then the next day there are 4. And I'm just like, that, okay, that's not right, guys. Somebody's filling out their paperwork in batches. That's a little more worrisome, especially when you're going to do this, right? This is today's RT. And you'll see when we actually spin this up why I'm kind of like, maybe not okay. Okay, back to TensorFlow. Okay, so there's R0, and then there's this number called gamma. So R0 is actually this amalgam of 3 different numbers. It's how long you stay infectious, it's how infectious the disease is, and it's this other number called gamma. Well, gamma is how long you stay infectious. And then it's how infectious the disease is. And then there are these other properties, and it's basically how fast you recover versus the time period that you're talking about. So we've smushed the time period down into 1 day. So we don't have to worry about days as much as we have to worry about the rate at which people are kind of coming into this infectious state and leaving it. And the infectious state then is how fast they're leaving is represented by gamma. It's this number called the serial interval. Now, Systrom just kind of declares that gamma is 1.7. And then he lets his estimate for RT represent all the other factors that have to do with how fast the disease is spreading, like social distancing measures, you know, our schools closed, that sort of thing. And so gamma is the serial interval, and he just declares it at 1 dot over 7 dot. You could extend this method to let gamma vary instead of letting R vary, but this actually kind of handles the situation for the purposes that he's using it for. Okay, so the magic formula calculated by Betancourt and Ribeiro, which is actually a very readable little paper, and I've linked to it here. All right, that magic formula says, okay, KT, so again, today's case count, is related to yesterday's smoothed case count based on this formula. You take gamma, the serial interval, you take RT, you subtract 1, you multiply it by gamma, you exponentiate that number, and you multiply it by KT. Okay? And you're probably sitting there going, I couldn't follow that, Melinda. Why? That's a whole lot of algebra to just say at me. That's okay. You employ a Python, if you're doing this for business, you employ a Python programmer and you say, this is the serial interval, give me a function. And that's what we're going to do, because this is TensorFlow and it's Pythonic. And it says, all right, I just build this little function that says, I'm going to give you a gamma, I'm going to give you an R, and you're going to return for me a case count. And that case count, you're going to return for me, I beg your pardon, an expected case count. Okay, so this is how you take current smoothed cases, your parameter called gamma, which we've just declared is 1 over 7, and your RT, and turn it into a lambda. The lambda becomes the function in your Poisson. Okay, so magic formula for turning R and gamma, which are things we know about the disease, into lambda, which is a parameter we need for the distribution. And now finally, we're going to start to write some TensorFlow probability code. Now, I'm going to walk you through this, but one of the things I really like about this is that it's pretty readable. So again, Systrom's code, he takes what he knows about Bayesian statistics, he takes what he knows about priors, etc., and he builds a Python function to calculate that, and he builds an outer Python function to kind of optimize through it. But here, if you know the mathematics, right, if you know how to build a Python function, or if you know how the function tends to be built, this little piece of code actually reads very similarly to how you would just kind of state how this works. So let's take a look. Okay, and it's Python, so I'm going to start on the inside, right? I'm thinking of a number that is distributed Poisson. To get the parameter for this Poisson distribution, I want you to run Melinda's magic function that she cribbed from a guy who's smarter than she is. Take this argument, which is RT, and that will give you your Poisson. So it's a Poisson with a lambda parameter that's equal to this fancy little function call. Okay. Well, for that I need RT. What's RT? Well, RT comes from this truncated normal. And the truncated normal is, I'm thinking of a number. I'm thinking of a series of numbers, in this case, that are distributed truncated normal. They all have the same mean. That mean is a number called P. They all have the same scale. That scale is 10. And I'm going to truncate it between 0.3 and 5. Okay. Well, what's P? Well, P is distributed normal between 2 and 1. Or P is distributed, normally distributed with a scale of 1. Okay. You can write these functions. You can just keep going. And you can write these as deep as you need to go. So this is joint distribution sequential. It literally says you're going to put together a sequence of Python functions. And Python functions, a sequence of TensorFlow probability distribution objects. The results from each one are going to feed into the next one and give you a new distribution. And TensorFlow probability is going to read that and say, okay, these are jointly distributed. I'm going to come up with a likelihood function with based on the fact that these are posterior distributions for different parameters. And I am going to, and I already know, I know what a normal distribution is. I know how to sample from a normal distribution, and I know how to calculate a log of the probability from a normal distribution. Talk about what a log prob is. Those of you who got excited when you heard that it could do its own log likelihood, you know where I'm going with this. If you didn't get excited, you will be in a minute. All right. This truncated normal, this tf.1 says give me a vector of ones, multiply them by p. So this says generate 46 truncated normal distributions. One line of code, 46 truncated normal distributions with a common mean that I'm going to pick on the fly. I've given you instructions, TensorFlow, just pick it. I'm going to take a draw from those 46 independent truncated normals. I'm going to shove them into this function, and I'm going to give you 46 Poisson distributions. Each of those is going to correspond to a time point. From time 0 to time number 46 of case counts that I have. Okay. I am literally going to...
Linda, just sorry to interrupt. And 46 is because you literally have 46 days that you've observed, right?
That is correct. 46 is because I literally have 46 days that I've observed. So I'm gonna literally calculate a parameter for every time point. That is the magic of Bayesian statistics. I'm allowed to do that. Okay. Other questions from the audience?
Everyone is in rapt attention.
Excellent, good. Okay. You can tell Melinda's a programmer, this isn't parameterizable enough. I've got to be able to do this for any number of time points I want. So I'm going to build a little Python function called build model. It's going to take how many time points I have, because different states have different numbers of time points. Okay. And it's going to build this little function from everything else. Okay. All right, rock and roll. So I run this function. So first off, I calculate in values. It's a new day, right? I ran this yesterday, I had 46. It's a new day, I've got 47. In values is gonna update because it gets the length of my tensors from above. And then I'm gonna run build model, tell it how many to give me, and distribution RT then becomes a TensorFlow object. This is a TensorFlow probability object from the class distribution. So it's not an equation, it's not a function, it's an object. And it's an object that knows things like, you're going to give me a value, Melinda, called x. X is distributed according to this other value called RT. RT depends on this parameter called P, and P depends on nothing. There are no inputs within my little function that I have. So this little resolve graph is a way to kind of query that object and find out what the dependencies are within the object. Oops, hang on. Okay. So resolve graph is a method for a TensorFlow probability object. It tells you what the dependencies are. But the TensorFlow probability distribution knows how to do a lot of things. And it's the fact that this little data structure, this little class, this little object from this class distribution knows how to do all of these complicated things That functionality is what lets me do all of this work with just a very few lines of code. So this distribution knows how to draw a sample from itself. Okay, I'll show you that in a minute. This distribution, so it knows how to give me values from the probability distribution. It also knows if I hand it a value, it knows how to calculate a log likelihood and the probabilities for that value. Okay. It can also do a lot of things that help you query that object to make sure that the object is working the way you think it should, which I'm not going to go into very deeply here, but to just kind of take a look at how amazingly powerful this thing is. So distribution RT is a TensorFlow probability object that describes all of those fancy relationships that I need in order to do this fancy math to calculate a daily RT. If I use the sample method, it literally draws a sample from itself. And so if I print it, that sample, well, think about what I told it to do way up here, right? If I draw a sample from this sequential distribution, that's not one number. That's a sample from a gamma distribution. That's a second sample from 46, 47 truncated normal distributions. And then it's another set of samples from, well, I put in 47 RTs, I'm going to get back 47 Poisson distributions, where, by the way, RT is this complicated number. So one sample from this is 1 plus 47 plus 47 numbers. And so when I say distribution RT.sample, I get a single tensor, which is a single value, which is the draw from that gamma. I get a second tensor, which is those 46 draws from the truncated normal, 47 draws from the truncated normal, and I get a third tensor that is 47 draws from a Poisson distribution calculated with a lot of inner logic that I don't have to think about anymore. I wrote it down in code. Hopefully I unit tested it. It's out of my life, right? I just say, okay, little RT, give me a sample. And RT says, very well, this is your sample. Okay. Questions there?
Nope, we had one question for the end comparing this to Pi MC3 or maybe Stan.
Sure.
Happy to take that at the end.
Yeah, we'll do that one at the end. Okay. Okay. So it knows how to sample from itself, which again, if you've ever had to write that little sampler in NumPy, that's life-changing. But it also knows, again, how to calculate a likelihood function when you give it a sample. So a tensor is a data structure. Okay, so if you're not a huge TensorFlow probability nerd, I keep saying the word tensor. A tensor is just a data structure that holds vectors. It holds as many vectors as you want. Those vectors might be vectors of vectors. And TensorFlow is all about having this nice language to manipulate those objects in a way that is sensible for problems where you're dealing with massive matrices of n dimensions and trying to make them talk to each other and do something like what we're doing right here, right? So I've got, like, in this case, I've got 3 arrays. One of them is an array of 1, right? Or one of them is an array that just has 1 number on it, but it's 3 arrays. 2 of them have to be the same size, right? There's all sorts of crazy stuff happening. TensorFlow has a lot of convenience functions that make that easy to handle. One of which is in TensorFlow probability is just being able to say, okay, I'm going to give you a tensor that has 3 tensors inside it. They're all going to be the right shape. So I'm actually going to call, so S equals distribution RT.sample. So S is another pole from the previous distribution. Okay, it's not the same one as before. And I'm going to put in the first value that got drawn, which was the gamma, or sorry, which was the parameter for the truncated normal. I'm going to put in the second value that got drawn, which was that massive vectors of RTs. And then I'm going to put in KT. Hold on, mind blown. Why did you put KT in? What's happening? The purpose of a likelihood function is to find the vector of parameters that are most likely given the data that you see. So I just randomly picked a P and a vector of RTs out of the air. But then I said, hold on, tell me the log of the joint probability distribution of this randomly selected P. These randomly selected gammas based on that P, and the data that I actually see, the data that actually exists in the world. Okay. Oh, well, Melinda, that number is minus 18,262. I want to maximize the likelihood, or I want to maximize the log of the likelihood because that's better numerically. This thing just calculated for me, given a draw from a distribution that I find sensible, it calculated the joint likelihood of those draws and the data that I have that is real in the world, right? My real data. So gosh, guys, wow, if you can do that, then probably you can come up with a set of tools that can take this little distribution object and find the best fitting values for all of that massive set of parameters that Melinda asked for, that crazy, crazy set of parameters, right? And that's what you do next, okay? Once you get that probability distribution settled in your mind, right? Once you are able to convince yourself and the people you work with that probability distribution is sensible and does what it's supposed to, now you can just take your data, take that tiny, tiny little piece of code that you wrote, right? That was a single cell on one screen, and say, TensorFlow, if you please, find the maximum likelihood estimators for P, which I really don't care about, right? For the mean of my distribution of RTs, and for my real-time RTs over time, okay? To do that, I need to tell it what the objective function is. This lambda notation, I find it really confusing, but basically what this says is, okay, you're gonna call distribution rt.logprob of something. KT is always the last argument. I don't want to think about how many other arguments I have to shove in at the front, so just, I'm going to call them X. That little asterisk says there's a ton of them, 2, 7, a million, I don't know. I'm going to give you a vector of RTs and a value of P. You're going to use my existing KT, and you're going to return to me the log likelihood, the joint probability distribution for those gammas and that K. Given my data then, please TensorFlow find the most likely parameters for this distribution. And now everything gets easy, all right? Everything gets easy, that's a joke. If you, if you've done Bayesian statistics, if you've used a product like Stan, or really Stan, WinBugs, right? PyMCMC, right? You know that setting up that MCMC chain is non-trivial, but there are a ton of tools in TensorFlow to set them up and make them work the way you want to. So so the really cool thing about this then is that I'm going to get a current state, right? You need a reasonable starting value for your MC chain. And I'm going to say, oh yeah, okay, well, tell you what, just start somewhere randomly. And I tell you what, just grab the last, just this :-1 says, I don't want the end, right? So pull another random sample from distribution RT. And then you can see, and that's going to be my current state. That's my starting point. And you can see, oh, awesome, right? I've got P, and I've got an array of gammas to get started. K is always the third argument. I'm not going to randomly sample. I'm going to give it my real data to calculate that objective function. And then I'm just going to tell it, all right, look, I want you to run, in this case, a Hamiltonian Monte Carlo. Why a Hamiltonian Monte Carlo? The great statistician wars rage on over Hamiltonian random walk. I guess everybody hates random walk by now, right? Whatever floats your boat on MC samplers, with step size adaptation, etc. Right? You can spend the rest of your life studying this, or you can just crib somebody else's code, which is what I did for this one. I'm going to run this Markov chain. I'm going to do a burn-in of 100. I'm going to ask for 10 to the E3 results, which are my samples. And as you guys know who do Bayesian statistics, right? So I've got this lovely way to figure out the likelihood function. But I'm not, when you're a Bayesian, you're not content with one value. When you're a Bayesian, you say, I understand that the world is random. And what I really want is a nice size sample of the parameters that make sense. And that's what an MC chain does. It tries to find a spot where it's sampling from that joint distribution in a way where you're in the most likely spot for this vector of 47 RTs. And that P, you're in the most likely spot to fit the data that you have. And it's going to sample from those distributions over and over again. And so the answer when you do Bayesian statistics isn't your gamma is 4 or your RT is 1. The answer in Bayesian statistics is, here's a whole bunch of RTs that are likely. Some are more likely than others. Here's the median, here's the range, here's the standard deviation, and we're going to plot them. And that's what happens when you do this run chain, all right? This is the Tensorflow sampler that's going to take that objective function I gave it. It's going to take that log distribution that I gave it. It's going to calculate that log likelihood function over and over again. It's going to find a good spot, and then it's going to start generating samples for me. And I've asked for 10 times 100, right? Then it's going to run the chain. It's going to give me the result in those samples. There are all sorts of diagnostics to make sure that your Markov chain has reached a reasonable space. You can get all of these in TensorFlow Probability. They pop out of this sampler in the same way everything else does. I'm not going to spend a whole lot of time there, because I find that when you teach that, you have to teach all the reasons why that's appropriate and all the ways to read the charts. There's tons of documentation on that. What I want to show you is why this is so great. I ran this last night with this many samples. It took like 5 minutes. I ran it this afternoon on my 10-year-old MacBook, and I asked for, I guess, an order of magnitude more, and it took about 20 minutes, okay? I'm not even using a GPU, right? This is just with my own little laptop. When I was in grad school, which wasn't that long ago, I would have had to have that run all night. Okay. And at the end, what I get, okay, I get this run of samples for my RTs, which are the things I'm excited about, right? And I'm going to look at the upper 95th confidence limit, the lower 95th confidence limit, the lower 5%. I'm going to get the mean. I'm going to pop those into a data frame. So remember, I've got 46 of them. I've got one for each time period in New York State. And it's Python, so in order to get a pretty plot, I have to crib somebody else's code. This is, again, Kevin Systrom's code. But check it out. For every time period in New York, I have a mean RT, right? That's an estimated mean RT. And I have error limits for RT, right? And they're pretty teensy. I'm actually not thrilled with this sampler. I don't think I'm sampling from the space as robustly as I can. But I could play with that sampler for the rest of my life, and I do have a job. Okay. But one of the things I think is really interesting about this is that, so this is the theoretical daily replication number for R. Okay. And you can see it kind of going along until March 17th, when everybody figures out that it's serious, and it drops. And then we start testing a little more robustly. It goes up again for a while. And now it's kind of moving up and down in the same spot. There's this big spike here. I'm pretty sure, again, that's more testing. There also seems to be a Monday effect on this, where maybe you're not filing reports as diligently over the weekend. That's my main criticism of this particular method, is that you really can't, is that it's really, really sensitive to changes in daily base count or daily case counts. And it's probably much, much better to do something that's a little bit smoother. However, you can also see that it's been coming down. It looks like it's about 0. The actual number is something more like 0.5. Just scale-wise, this plot makes it look like it's super tiny. Also, again, we have an early in the week effect. But you can see, and this is about the point where we predicted that New York was going to start to level off, right? Things were going to start getting better in New York about mid-April, and it looks like that's what's happening. Systrom actually does this for everybody on his blog. He does this for all 50 states and does this really nice scatter plot. He's got, and again, this is a different method. He uses the highest density interval, which he kind of gets by trying a bunch of different R's and getting the ones that give him the highest likelihood function. You can do that when you're only dealing with like 40 time points. Okay, and you can see NC, and this happened in a lot of places where it got really low for a while and now it's bumping back up. And again, I think that's testing. All right, okay. And, you know, again, kind of the idea of Bayes is that you get this idea of the size of the problem, is how different it is, or the size of the problem, the true variance in your parameters. Typical frequentist methods, I'm going to pop out a parameter estimate, as many parameter estimates as you asked for. I'm going to pop out an estimate for the variance, but the estimate for the variance is based on a lot of assumptions. These are based on different assumptions. But if you take a look, now this is New York State only, right? These are the P parameters, that sample 0 that comes out of that TensorFlow probability. You can see that there are 3 distinct distributions, right? But they're always around 2-ish for New York. Okay, so that kind of mean of that truncated normal. You could not do this with a frequentist package. You could do it with a lot of any good Bayesian package will give you this number. I've never picked up a Bayesian package as quickly as I've learned TensorFlow. And I think that is mostly because, and this is why I'm so excited about it, I really feel like TensorFlow probability was built with the end in mind. That somebody said, I want Melinda Thielbar, who's a decent programmer, but she's better at math. I want Melinda to be able to spin something up on a Jupyter notebook that she can test. I want to eliminate all the work she has to do that she's not very good at, like remembering that you can't, like remembering all the places where you can do a numerical overflow and calculating a gradient for every single probability distribution in existence, and figuring out how to set up a Hamiltonian sampler. Oh, wait, no, this other customer wants a random walk sampler because they just think that's the bee's knees. They're all there. They're all there. It does all of that messy differentiation, matrix math differentiation that you would have to do if you wanted to do a custom distribution. That is done inside TensorFlow. It's generally not numeric. And if you have something super fancy that you want to do that they don't have, you can code it yourself. You can inherit from their distribution class. You can provide the information that you need, and you can roll with it. Okay. What are the downsides? You still need to know some math. This will not save you. If you want to do Bayesian statistics, this will not save you from needing to learn all the wacky stuff you need to know for Bayesian statistics, including how to set up your samplers, how to do the estimation. That stuff is still, that work is still there for you to do. TensorFlow Probability is still, right now it's at a 0.9 release. It doesn't have a lot of the convenience features that you would probably want if you're not a huge Python programmer. If you are already familiar with TensorFlow, I think TensorFlow Probability probably makes a lot of sense. If you're not already familiar with TensorFlow, it's a bit of a learning curve. If you don't know Python and you have never used TensorFlow, it's probably a lot of work. It's probably a pretty steep climb. And I would say that's the biggest downside to the language right now. Other upsides though, again, this thing is GPU enabled out of the box. The setup, like the setup that your IT people have to do to run massive models is still there, but you don't have to change all your code when somebody suddenly, when you're suddenly like, okay, I want to do this on a massive problem and in parallel. So there is at least that, right? If you want to run this at scale, it will run at scale, and you don't have to make a lot of changes to how you calculate your math. The really, really exciting stuff is the stuff that you can do with TensorFlow. So all of the things that we know about TensorFlow with building neural networks and these fancy, fancy models with these super flexible structures, you can channel all the results from those super flexible structures and those many, many layers and say, I'm pretty sure that at the end of the day, the stuff that I'm predicting is normal with a, or is normal or has a Gaussian process underneath it. And so I feel like a lot of machine learning focuses super hard on getting a point estimate, right? Is Melinda gonna leave her job this week or not? Is Melinda gonna respond to my credit card offer or not? Is Melinda gonna wreck her car over this year or not? What TensorFlow Probability lets you do is take all of that machine learning stuff and say, well, maybe Melinda's gonna wreck her car this month, but she's not on the road right now. And also on a normal week, my error bars around that probability are somewhere between 0.1 and 99. So technically I don't know, right? And the flexibility to code that into your model is what really makes this exciting and what really makes this run. Okay. There are a ton of useful packages. A lot of these are new and I have not spent a lot of time with them, but there is a GLM package. Linear mixed effect models are the first thing that you want to do when you get your hands on this. If you're a stat nerd like me, the first thing I'm looking for is, can I do a linear mixed effect model? Why, yes, you can. There is a there's a book called Bayesian Methods for Hackers. It was originally done using PyMCMC, and the TensorFlow Probability guys took all the PyMCMC examples and did them in TensorFlow probability. So what I would say for those of you who are asking about PyMCMC is I would actually take a look at examples and see what it's like to code that stuff up in PyMCMC and compare it to what it's like to code that stuff up in TensorFlow probability. And, you know, make your own judgments about which one is easier and which one is more conducive to your process. Okay, I'm going to stop there and answer questions. And yeah, that's what I'm going to do. So questions.
There were a couple that came in. One, just the first one, maybe it's a softball. When you had all those straightish lines going through your initial heteroscedastic example, and then you put the kind of very wiggly red line that did a much better job of catching the wiggliness of those dots. How do you know that's not just overfitting, right? Like I could have just connected the dots.
Yeah, no, that's a reasonable question. And I would say if you're, it's actually right here. So you would have to have some mathematical knowledge that this is what you should do, is what I would say. I would not decide to fit that squiggly red line based on that scatter plot. I would decide to fit that line based on some like statistical or mathematical understanding of the underlying process.
Awesome, thanks. There was another question about why would you say there's so much more variability in your RT across time for New York compared to what was in Systrom's article?
So Systrom is piling up the likelihood functions over time. So he gets a smoother and more certain RT at each of those time points. So I mean, his is an actually completely different optimization from what I'm doing in TensorFlow. And you could argue that it's better to kind of window that likelihood function because this is a time series problem. It's better to kind of window that likelihood function than to do what I'm doing, which is just saying, okay, today's smooth cases predict today's new cases, end of story. Tomorrow's predict tomorrow's. He actually windows the likelihood function over time, which is a pretty slick way to do it.
That makes sense. Awesome, thanks. There was this kind of, I think, platform-specific question. Do you know if anyone's tried getting TensorFlow probability to work with my binder? There's like I think Git for notebooks, Git for Jupyter notebooks, binders of notebooks. I might be misrepresenting that, so if someone wanted to unmute and correct me, that'd be fine.
Yeah, and I'm going to go ahead and stop share. I can always share again if I need to. So my guess, right, is that, and if somebody knows, please share in the chat. My guess is Jupyter has its own thing, or not Jupyter, sorry, Google has its own thing called Colab. They've got their own kind of network, or they've got their own kind of notebook system that looks like a Jupyter notebook, but it runs in their cloud and blah, blah, blah. So what it looks like to me strategically is that while Google is committed to open source, they've got some special bells and whistles so that if you're using their cloud, you get some extra, some things are just easier for you. And one of them looks like the Colab notebooks, just run better with their stuff.
That makes sense. And that Colab, I know they offer some free access. There's a free tier that even has like GPUs available, which is a pretty sweet deal. And then I chickened out because it was a long question. Well, that was the one that I kind of chimed in with earlier, the PyMC3. I'll just read it to you. This seems very similar to probabilistic programming with PyMC3. And in fact, the TensorFlow Probability site links to their own version of a PPWPMC sorry, tutorial. And then the link, of course, is in the chat.
Yeah, and it's the same idea as PyMCMC. And like I said, Bayesian Statistics for Hackers was originally written for PyMCMC, and then they just redid all their examples in TensorFlow. The joint sequential distributions. I love Dan's background. That is the best. The joint sequential distribution, which was the distribution I was using for my R's, you would have to code that by hand. TensorFlow Probability is the only thing I know that has that as readily available, where you just kind of tuck it all into one big function. It's not hard to code those likelihood functions if you're familiar with them, but it is an extra step.
Awesome, thanks. There might be another question or two in the chat that I missed at the end there.
Sure.
So maybe like whistle a Disney song, so they'll pull the whole video down, and I'll.
And it looks like some folks are actually working on the. Looks like some folks are working the problem with me on PyMCMC. Oh. Okay, I'm comfortable with unmuting and just going from there, guys. So like we don't have to kick everybody out at this point. This concludes my presentation. You will not hurt my feelings if you drop off at this point. I really appreciate everybody hanging out with us in your living rooms on a Tuesday night. Eric, are there any announcements we need to make or anything like that?
Not at the moment. Still in a holding pattern.
I have a question, Melinda. Do you know if there's generalized additive modeling capabilities?
I do not know.
Okay.
I do not know. They've added a lot of functionality since I started putting this talk together. Like the GLM stuff, the structural time series stuff, as far as I can tell, is new since I started learning TensorFlow. So that's how fast this is moving.
Yeah. Okay, thanks.
Yeah.
It's good talk.
Thank you. Okay.
Awesome. Well, thanks again, Melinda, for your time and your expertise. And thank you, everyone, for participating in the inaugural Research Triangle and anyone else with an internet connection analyst monthly meeting. It's been a real pleasure. And if you have any questions or anything, you know where to find us all. And we look forward to the next time. We'll be in touch.
Thanks, everybody.
Thanks, Melinda.